We're going to end the course today by hitting on some topics from Chapter 28 on alternating current circuits and Chapter 29 on Maxwell's equations. So first, let's talk about alternating current. As we learned in the last chapter, simply taking a loop of wire and spinning it in a magnetic field will produce an alternating current. And so here we have that. We have that if the peak voltage is Vp, that the voltage is going to oscillate between negative Vp and Vp. Again, in our country, the frequency with which we rotate our generators is 60 hertz. So we have a 60 hertz sine wave coming out of our outlets. Now, if the voltage looks like that, then the current is also oscillating. And again, that's why we call it alternating current. It's both alternating current and alternating voltage, obviously. And so here, if the resistance is R, then we can write the current in terms of the peak voltage and the resistance, and we can just give that peak current a name, IP. All right, so we want to look at this in a little bit more detail. And specifically, based on what we've seen so far, do you think that the peak voltage is 120 volts? Because in everyday speech, when we talk about the voltage coming out of a wall outlet, we say it's a 120 volt outlet. Well, it turns out that what's actually coming out of the wall outlet is a peak voltage of 170 volts. So if you measure, if we hooked an oscilloscope up to an outlet and looked at the waveform, we would see that it's going from negative 170 volts to 170 volts. So the question is, why do we say that the voltage is 120 volts? Well, that's what I want to get into over the next couple slides. But the key thing to understand is that an AC voltage that oscillates between negative 170 and 170 volts provides the same average power, and I really should have the word average here, as a DC voltage of 120 volts. So that 120 volts is really the DC equivalent of what's actually going on in the outlet. So let's see where that comes from. Think about the power delivered by an AC voltage. We know that power is current times voltage. And so if we look at the expressions that we had on a couple slides ago, we said that the current is the peak current times the sine of omega t, and the voltage is the peak voltage times the sine of omega t. So in other words, the power delivered is just peak current, peak voltage, times the sine squared of omega t. So what does that look like? Well, here would be the power. In other words, here's peak current, peak voltage versus time. And what we want to understand is, what is the average power delivered by that? Well, you'll notice that for every peak above this line, there is an equivalent missing piece here. And so pretty quickly you can understand that the average power delivered by an AC voltage is simply 1/2 the peak current times the peak voltage. Okay, well, the thing is, we want power to be just current times voltage, right? Because that's our definition of power. So we want to rewrite this using new terms. So we're going to define something called the root mean square of the current and the voltage. The root mean square of the current is the peak current divided by the square root of 2. And the RMS voltage is the peak voltage divided by the square root of 2. So what I want to show you is that if we define the current and the voltage in this way, then the average power is just equal to IRMS times VRMS. because you'll notice that's peak current divided by the square root of 2 times peak voltage divided by the square root of 2, which gets us back to the 1/2 peak current, peak voltage. So IRMS and VRMS, those are essentially the DC equivalents for an AC circuit. And you'll notice that if we calculate what is VRMS, we take the peak voltage divided by the square root of 2, or 170 volts divided by the square root of 2, and that is 120 volts. So when we say that the voltage is 120 volts coming out of the outlet, that's the RMS value. In other words, essentially, that is the DC equivalent value of an AC voltage that goes between negative 170 and plus 170 volts. By the way, if you think back a few chapters to when we were talking about household circuits and safety, all the numbers that I used in that chapter were RMS values. So for example, when I told you that a typical household circuit has a circuit breaker of 15 amps or 20 amps, what I'm telling you is that the root mean square of the current can be up to 15 amps, or the root mean square of the current can be up to 20 amps before that circuit breaker blows. The peak current is actually higher because, again, we have this formula. All right, so generally, when we're dealing with AC voltages and currents, we can kind of use the RMS values and then essentially treat them like they're DC circuits. Here's a question that I asked earlier in the course. Why do we use AC? And it's really kind of a two-part answer. The first part is we've got to understand, is it better to transfer power at high or low voltage? Now, you probably all know the answer to this because we've all seen high voltage power lines. So we know that we transfer it at high voltage. There must be some reason that that's better. Let's see why that is. First of all, remember, power is current times voltage. So really what we care about is how much power gets to our homes, right? How much energy per time gets to our homes. So here is a very simplistic version of the power grid. Only your home and the power company are on it. Let's say the power company is putting out a voltage, VPC for power company, and your home effectively has a resistance, little r, and we're going to be sending current back and forth through our power lines. Now, because the power company is far away from where we live, we can't assume that the resistance of our power lines is 0. It's not. So we're modeling this as thinking about it like there is a series resistance of capital R. That's the resistance of the power lines. What I want to figure out is what percent of power do we lose? So what's the percent of power lost as we send our power from the power company to your home? Well, the power that we lose is simply the power that's lost across the resistance. So we know that the voltage across the power lines is just whatever the current is in the circuit times the resistance of the power lines. So the power that we lose is just the current in our circuit times the voltage drop across the power lines. Well, the total power that we put out is just the current times the voltage put out by the power company. Well, VPL I can rewrite as I times R. So you'll notice the top here I get I squared R, and on the bottom I get I times the voltage being put out by the power company. That square cancels with that, and you'll notice that the percent power lost is directly proportional to the current that we're passing through our grid the resistance of the grid, and it's inversely proportional to the voltage that the power company puts out. So you'll notice if we want to lose a smaller percentage of the power, we want to minimize the current. Obviously, we want to minimize the resistance of the transmission lines, but there's only so much you can do for that. And we want to maximize the voltage put out by the power company. Okay, so we want to transfer at high voltage. Why does that mean we need to use AC? Well, here's the problem. We want to transfer our power at high voltage, but we don't want people to have to use it at high voltage. You don't want your kid going over and plugging into a 100,000 volt outlet because they could get electrocuted much more easily with a higher voltage. And so we need a way to be able to convert from high voltage to low voltage so that we can transfer our power at high voltage, but then we can decrease it to a low voltage right where we use it. Well, that's what a transformer does. Remember, a transformer is an example of Faraday's law. We talked about it in the last class. The way you make a transformer is you just have a core of iron, and we have two coils. There is no electrical connection between this coil and this coil. As long as I have an alternating current go into the primary coil, then it will produce a changing magnetic field. Well, that changing magnetic field will go back and forth through the secondary coil. And from Faraday's law, we know a changing magnetic field produces a voltage. Notice, though, if we put a DC voltage in instead of an AC voltage, this would just create a constant magnetic field. Well, a constant magnetic field through a loop doesn't do anything. So we have to use AC because we need to be able to use transformers, and transformers only work for AC. That's the reason we use AC power. Let's talk about transformers a little bit. It turns out that the formula that describes transformers is very, very easy. It simply says that the voltage you get out compared to the voltage you put in is equal to the ratio of turns in the secondary to the ratio of turns in the primary. Okay, so notice if I have twice as many turns in the secondary as I do in the primary, my voltage is going to be doubled. Now, you might be looking at that and saying, well, wait a minute, wouldn't that violate conservation of energy? And the answer is no, because a transformer does not change the power. In other words, the power that goes into the transformer is equal to the power that comes out. Now, in reality, the power that comes out is actually a little bit less because you do lose some energy in a transformer. You may have noticed if you feel like the charger block of your cell phone or of your laptop, that they feel warm. What's in there is a transformer, and if it feels warm, it's losing some energy. So at best, we only get the same amount of energy per time out that we put in. And in the real world, we actually get a little bit less. Okay, so notice then that if I have a transformer that increases the voltage, it correspondingly decreases the current so that the power doesn't change. So we don't violate conservation of energy. Let's do a simple example here. It says a transformer is designed to convert 120 volts to 240 volts. If the primary has 2,000 turns, how many turns should the secondary have? And if the current in the primary is 10 amps, what's the current in the secondary? Okay, so you can probably just figure this out in your head, but let me write it out with the formulas. Again, here's our transformer. We've got a number of turns in our primary and a number of turns in our secondary, so that's N1 and N2. And we know that the ratio of the voltages is simply equal to the ratio of the number of turns. In this case, we're trying to figure out how many turns we should have in the secondary. So N2 is going to be equal to V2 N1 over V1. or 240 times 2,000 divided by 120, and that is 4,000 turns. The second question was, what is the current in the secondary? Well, since the voltage got the voltage got doubled, we know what's going to happen to the current, right? It's going to get halved. But let's write it out with a formula. I1 V1 is equal to I2 V2. So the current in the secondary is just I1 V1 divided by V2, or 10 amps times 120 volts. Divided by 240 volts, or 5 amps. Okay, so the voltage doubled, so the current had to be cut in half. The last slide on information from chapter 28 just kind of shows you how this actually works in the power grid. So again, we want to transfer our power at high voltage because we lose the smallest percent of the energy that way. So at the power plant, we've got generators. They're going to generate electricity at a pretty high voltage. But then before transmitting over long power lines, we actually use what are called step-up transformers to increase the voltage even more. Again, increase the voltage, decrease the current. You know that the more current you put through a wire, the easier the wire heats up. So just conceptually, it makes sense that we want to keep the current as small as possible while being able to transfer the power that we need. So the voltage, once we're transferring over the power lines, is very high, hundreds of thousands of volts. But again, we don't want to use the voltage at that level because it'd be way too easy to get electrocuted. So usually in your town, there is the substation where that voltage gets transferred from that really high voltage down to just a few thousand volts. And so the power lines that go through a neighborhood, for example, are still at a couple thousand volts. The final step down to the 240 volts that comes in to your place of residence doesn't happen until right before it enters. So I'm sure you've noticed these big gray cans that are up on about every third telephone pole or so. Those are the final step-down transformers. That's where the electricity is stepped down to the 240 volts that actually comes into your house. Now, if you live in an apartment complex, what you'll often will notice is there are these big gray or green boxes like next to the building or behind the building. In fact, if you think about at Middlesex, behind Henderson Hall, you may have noticed these big boxes. Those are the step-down transformers when you're looking at a apartment complex or a bigger building. That's what they look like. Okay, so that's why we have to use AC, because we've got to be able to transmit at high voltage. We want to be able to use it at low voltage. And transformers allow us to change the voltage, but they only work with AC because of Faraday's law. Let's look at our final chapter of the course, which is chapter 29. Here we're going to kind of tie together everything that we've talked about. So we know that electromagnetism is one of our four fundamental forces, along with gravity, the strong nuclear force, and the weak nuclear force. And Maxwell's equations, the four equations that we've talked about, along with the Lorentz force, and by the way, the Lorentz force is just a fancy term for combining the force of a charge in an electric field and a magnetic field, which of course we've talked a lot about. So Maxwell's equations completely describe electromagnetism, and we've already learned them all. Gauss's law for magnetism, Ampere's law, and Faraday's law. The key thing about Maxwell's equations is that together they predict the existence of electromagnetic waves. And we talked about electromagnetic waves earlier in the course, and we'll return to it over this last number of slides. Now, the question that you might have is, why do we call these Maxwell's equations if he didn't actually make up any of them? That's kind of a neat trick, right? Put your name on equations that somebody else came up with. Well, it turns out that Maxwell does deserve the credit that he gets, because he's the one who figured out that together these four equations tell the story of electromagnetic waves. Now, the only way that they tell the story is we have to realize one of the equations, as we've learned it so far, is not quite right. It's incomplete. And the person who figured this out was Maxwell. So Maxwell realized that Ampere's law was not quite complete. There was a term missing. Now, for the examples we used Ampere's law on, not affected by this. But Maxwell figured out there was something missing. Let's look at the thought process that he went through to figure this out. In order to understand this, we've got to understand something about capacitors. And the good news is we've pretty recently covered capacitors. If I put a DC voltage into a capacitor, like a battery, well, notice this is just an RC charging circuit. The instant that I connect that, we know the voltage across the capacitor is initially 0, which means all of our voltage is across the resistor. But as the capacitor charges up, the voltage across the resistor goes to 0. So remember, this is what the voltage looks like across the resistor, where this is the voltage in, or the EMF of the battery. Okay, so a capacitor basically blocks DC current. Once it's charged, nothing gets through it. But let's look at what happens if instead of a battery here, I put an AC voltage. So I put a voltage in that looks like that. Well, you'll notice that the capacitor will start to charge, but then an instant later, the current is changing direction. So now the capacitor discharges, and then it charges, and then it discharges. So we're going to get a constantly changing current through the resistor. So if we look at the voltage out across the resistor, we now get a voltage that looks very much like what went in. Now, in terms of how big that voltage is compared to what went in, that's determined by the values of R and C. But all we care about is understanding that that capacitor does not block an AC current, because the AC current is constantly changing direction, and the capacitor is happy to just charge and discharge. And so current is constantly flowing in that circuit, unlike in this one where the current goes to 0. Okay, so let's remember what Ampere's law talks about. It says that if you integrate the magnetic field around a closed path, what you get is equal to mu naught times the current enclosed in the path. Okay, so here's the path, and if I look at the current crossing that path, it's just the current in this wire I. But here's the thing about Ampere's law. It doesn't have to be this area. It really just mathematically has to be an area bounded by this path. So you'll notice surface 2 could be the area that we're talking about, where the current goes through. But you'll notice it still works fine, because whether I'm talking about the current going through this area or the current going through this area, it's still I in each case. So Ampere's law works no matter which of those areas we talk about. But now what Maxwell did was he pictured looking at this in an RC circuit. And he said, look at what's going on here. If I talk about this being the area bounded by my path, there is definitely a current I going through that area. But if my area is now this surface, surface 2, Notice there is no current going through that because surface 2 passes through the capacitor. Well, Ampere's law still has to be true, but now there's no current going through that surface, so something's wrong. Well, here's what he concluded. That not only does a current create a magnetic field, but a changing electric field, which is what we'd have inside the capacitor, must also produce a magnetic field. And so Maxwell corrected Ampere's law, so it now looks like this. And so here is the term that Maxwell added. You'll notice that we have a changing electric flux. In other words, if there's a changing electric field in a region of space, that will create a magnetic field, just like a current will create a magnetic field. And it turns out that was the big missing piece in putting all of these equations together. So let's look at Maxwell's equations now in all their glory. So here they are. For the final, I want you to be able to conceptually understand what these mean. So I'm looking for conceptual, let me write it this way, I'm looking for conceptual understanding. And I'm also hoping my pen will start writing. So I'm not going to be asking you to solve big complex math problems with these. I want you to understand what they represent. So let's look at Gauss's law. Think about, what is Gauss's law telling you? See if you remember. Well, hopefully you came up with this sentence. Electric charges create electric fields. If I have an electric charge in a region of space, it creates an electric field. Okay? So charges create electric fields. That's what Gauss's law for electricity is saying. Let's look at Gauss's law for magnetism. What is Gauss's law for magnetism saying? There is no such thing as magnetic charge, or what we refer to as magnetic monopoles. I never have just a north or just a south pole. Okay? So electric charges create electric fields. There is no equivalent stuff that creates magnetic fields. Faraday's law. Faraday's law, as we learned in the last chapter, tells us that a changing magnetic field will produce an electric field. Okay? Now in the last class, we talked about getting an induced voltage. But remember, fundamentally, that means it's creating an electric field. So changing magnetic fields create electric fields. And then finally, for Ampere's law, moving charges, in other words, currents, or changing electric fields create magnetic fields. So that's the story that Maxwell's equations are telling you. Now, one of the things that's kind of interesting about this is notice that there is sort of an asymmetry among these equations. We've got one term here, we've got two terms here. We have something here, we don't have something here. What's kind of cool is if magnetic monopoles are eventually discovered, we know exactly where they go, theoretically, right? We would now have magnetic charge, so we would have something here. And if moving electric charges create magnetic fields, then moving magnetic charges would create electric fields. So if we had monopoles, then these equations would be completely symmetric, okay? Completely symmetrical. But that's why they're not, because there are no known magnetic monopoles. Okay, so this is the understanding that I'm expecting of you for the final exam. Now, the next thing I want to do is I want to look at the special case of what Maxwell's equations look like in a vacuum. So in other words, if we're in the vacuum of space and there are no charges around, so then there are no moving charges around, you'll notice that both Gauss's law and Gauss's law for magnetism are just equal to zero, saying that there are no charges of either type around. But notice what Faraday's law says. It says even if we're in the vacuum of space, if I have a changing magnetic field, I'm going to get an electric field. And if I have a changing electric field, I'm going to get a magnetic field. So remember, we didn't have this term except for Maxwell. So what did Maxwell conclude from this? What he realized is that a changing electric field is going to produce a magnetic field, but that's going to be changing. But a changing magnetic field produces a changing electric field, but that produces a changing magnetic field. Well, what he realized is that predicts that there should be these self-propagating things called electromagnetic waves. Now remember, this is before anybody knew what an electromagnetic wave was. This is before we knew light was an electromagnetic wave. Maxwell just figured out there should be these things called electromagnetic waves. That was his key insight. Now I want to just remind you of stuff that we talked about at the beginning of the course. Remember, we talked about waves traveling on a string, and we said that this is the equation that describes a wave traveling on a string. Remember, k is the wave number and omega is the angular frequency. And we also saw that the velocity of the wave is the wavelength times the frequency, which you can also write as omega over k. So here's the great thing about physics. You figure out something in one area of physics and it applies in a different area. Maxwell was able to predict that there should be these things called electromagnetic waves, and not only that, but the equation that describes a simple electromagnetic plane wave should be exactly the same as a wave on a string. In other words, here's our wave on a string equation, and the only thing that's more complex for an electromagnetic wave is that instead of just one thing waving, we have two. We have a magnetic and an electric field that are always perpendicular to each other. Okay? But notice this is just the peak value of the electric field and the peak value of the magnetic field, which is just the same meaning as the amplitude of a wave on a string. Otherwise, mathematically, it's described exactly the same way. So that's what Maxwell was able to show once he fixed Ampere's law. But even more remarkably, Maxwell was able to show that the speed of an electromagnetic wave should be related to mu naught and epsilon naught, those two fundamental constants of electricity and magnetism. And so why don't you go ahead and calculate this, see what you get if you take 1 over the square root of 8.85 times 10 to the negative 12th times 4 pi times 10 to the negative 7th. Well, hopefully what you get is 3 times 10 to the 8th meters per second. So think about this. Maxwell was not only able to predict that electromagnetic waves should exist, but he was able to predict the speed. And we now know, of course, that he was right. Let me remind you of some stuff we talked about way back at the beginning of the semester. We talked about the electromagnetic spectrum. By the way, I do want you to still know this for the final. And so we know that all parts of the electromagnetic spectrum have the same velocity, c, 3 times 10 to the 8th meters per second. And the only thing that differentiates one region of the spectrum from another is the relative size of the wavelength and the frequency. Okay, so up at this end, we have high frequency, short wavelength. Down here, we have long wavelengths and low frequencies. Remember also that that electromagnetic waves interact in terms of bundles of energy called photons, and that the energy of an individual photon is related to Planck's constant and the frequency. So you'll notice that a gamma ray photon has a lot more energy than a radio wave photon. And that's why X-rays and gamma rays can hurt you, because each photon has more energy and can damage, inside the cells of your body. Whereas a radio wave photon has so little energy, it's going to just essentially bounce off. The last thing I want to just remind you of is how electromagnetic waves are created. We know that in general, any kind of wave is caused by some kind of vibration. Electromagnetic waves are caused by accelerating electric charges. Remember, they could be accelerating back and forth, up and down like in an antenna, or they could be accelerating in circular motion like how we create microwaves in a microwave oven. But as long as the charges, and usually it's electrons, as long as the electrons are accelerating in some kind of a periodic way, whether back and forth or around in a circle, that's going to create an electromagnetic wave. And as the final thing, I'm going to actually bring up this simulation and show you what this looks like. So here's the simulation. We've got a radio antenna over here. And right now I just have the static field being created by this one electron. So you'll notice whether that electron is stationary or moving, it's not really changing the electric field in any significant way. But what we now want to do is we want to see what happens when I actually wiggle that electron and I look at what is the electromagnetic wave that gets created. So if I just wiggle it up and down, you'll notice just in that amount of time, it created this oscillating electric field. Now, what the simulation doesn't show you is the magnetic field that's associated with it. But any kind of a motion creates a propagating electromagnetic wave. If I want to make this more continuous, I can say oscillate. And now we can see the electric field wave that is propagating out from that charge. And again, there would be a perpendicular magnetic field associated with it. They just don't try to draw that because it gets too messy. But that's our electromagnetic wave that's propagating out through space.